Hi, welcome to Antiderivatives and Indefinite Integration. This is actually part 2. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso, my full-time job, and an assistant professor at Doña Ana Community College. This is integration, part 2, more examples. This time we're going to look at some antiderivatives, and then we're going to find the derivative of our, quote, answer and make sure we're right. Let's take a look. So, we're going to find the indefinite integral by, and then check our result by differentiation. We have the antiderivative of 12 minus x. Notice the use of parentheses to keep it all together here. The antiderivative of 12 will be 12x minus the antiderivative of x. We add 1. So, add 1 to the exponent. 1 plus 1 makes 2. Divide by that new number. And don't forget the antiderivative. We always have a plus c. Now, I want to check my answer. Check the result. So I take my result, take my answer, and I'm going to find the derivative. What's the derivative of 12x? It's 12 minus sign. What's the derivative of x squared over 2? This is not the quotient rule. There's no derivatives in the denominator. So the derivative of x squared over 2 is 2x over 2. Plus, the derivative of constant is 0. 12 minus 2x over 2 is 12 minus x, our exact integrand. So we know our integral is correct, antiderivative, because when we check it with the process of differentiation, we get back to the original. Problem number 2. The antiderivative of 8x cubed minus 9x squared plus 4 dx. We take each individual integral, right? We had a sum and difference rule that allows us to go through. We had a constant multiple rule that allows us to ignore the coefficient at first. So we have 8x cubed. We're going to keep the 8 constant. The antiderivative of x cubed is x to the 4th over 4. Remember, we add 1 to the exponent, divide by that new number, minus 9. The antiderivative of x squared is x cubed over 3. Add 1, divide by that new number, plus the antiderivative of 4. Remember, what has derivative equal to 4? That's right, 4x does. The antiderivative of a constant dx is kx. So we go backwards on that rule, plus c. Simplify, 8 over 4 is 2. So that's 2x to the 4th minus 3x cubed plus a 4x plus c. I check it. I take my answer. This is my answer of the antidifferentiation. I take my answer and I find the derivative. The derivative of 2x to the 4th is 8x cubed. Minus the derivative of 3x squared is minus, let me say it correctly. The derivative of minus 3x cubed is minus 9x squared. The derivative of 4x is 4. The derivative of the constant is 0. And I have my original integrand back. So I know it's right. Now this process of differentiation, you could do it any time and make sure you're correct. Hint, hint, like maybe on an exam. Great time to check your work with this process. Number 3. The antiderivative of the square root of x plus 1 over 2 square root of x. The first thing I'm going to do is rewrite. So the square root of x, that's x to the 1/2. The 1 over 2 is a 1/2. The square root of x in the denominator becomes x to the negative 1/2. That way I'm not dealing with any denominators. The antiderivative of x to the 1/2 is x to the 1/2 plus 1 divided by that new exponent plus 1/2 out in front. The antiderivative of x to the negative 1/2 is negative 1/2 plus 1 is my new exponent and my new denominator. Plus c. Remember, I write plus c at every step just so I don't forget it in the end answer. 1/2 plus 1 is 3/2. Negative 1/2 plus 1 is 1/2. So my first step, don't forget the plus c. Dividing by 3/2 is the same as multiplying by 2/3. So this will be 2/3 x to the 3/2. My 1/2 and dividing by 1/2, so that's multiplying by 2. So I have 1/2 times 2. That makes a 1, x to the 1/2 plus c. And see this little asterisk that I kind of skipped over? That is, I'm tired of typing the derivatives. You could check this if you really wanted to, and maybe I will do it right here. Taking our integral as my answer, and I find the derivative. So I'm going to call that, we'll call that capital F prime. And that'll be 2/3 times, bring down the 3/2, x to the 3/2 minus 1. Yeah, my writing's just amazing today. Plus the derivative of x to the 1/2 is 1/2, x to the negative 1/2, and the derivative of a constant is 0. Notice that this makes 1. I'll have x to the 1/2, and this is 1 over 2 square root of x, the original that I had here. So it all works out. I won't be doing the derivatives anymore as the check, but I did show you the model for it and how you can do that work if you need to. Hit pause, check, make sure I'm right. I make mistakes and they're never on purpose. If we have a quotient as our antiderivative at this stage in Calculus 1, we don't have a quotient rule, and we're not ever going to have a quotient rule, don't get me wrong. We're not going to have a quotient rule just magically appear in Cal 3 or anything like that. But we'll have other techniques we could use later sometimes to deal with these quotients. We'll use trig substitutions, we'll use integration by parts, we'll do some fun things. Seriously, you get some amazing tools later on, but for now, nothing we can do but suck it up and divide. So I take this integrand, right, the thing inside the integral, and I divide. I take x squared over x to the 4th plus 2x over x to the 4th minus 3 over x to the 4th, and I simplify. X squared divided by x to the 4th is x to the negative 2 plus 2x to the negative 3 minus 3x to the negative 4, and I can integrate that. Okay, we don't have a quotient rule. We're never going to have a quotient rule. So we simplify our integrand so that we don't need a quotient rule. The antiderivative of x to the negative 2, I'm going to add 1 to the exponent, divide by that new value, plus 2, so I leave the 2 alone, x to the negative 3. When I integrate, I add 1 to the exponent, divide by that new value, minus 3, the constant stays the same, the coefficient. X to the negative 4 has an antiderivative of x to the negative 3 over negative 3. Remember the new exponent, we add 1, and then we divide by that same value. Let's tighten it up here. This is a negative 1, x to the negative 1, so the negative exponent takes us to the denominator. The negative 1, that's just a negative 1. 2 over 2 cancels, but the negative sign remains. X to the negative 2 is 1 over x squared. Couple of negatives here make a positive. The 3 over 3, they cancel out. I'll have plus 1 over x to the positive 3 plus c as my antiderivative. Again, you may always check it by differentiation. I'm just not going to type that out. Here we see that t is our variable of interest. No product rule. Well, we kind of have a chain rule for our integrals, but it's not going to apply in this case. So what we're going to have to do for 2t squared minus 1 all squared as an integrand is we multiply it out. Make sure you use FOIL. Don't just square the ends. You'll miss out the good middle terms. So now I can integrate. The integral of 4t to the 4th minus 4t squared plus 1 will be, dt, will be 4t to the 5th over 5 minus 4t cubed over 3 plus t, right? The antiderivative of 1 is t, because t is our variable, plus c. And I simplify it just a little bit. Instead of calling it 4t to the 5th over 5, maybe you prefer 4/5 t to the 5th. This is a fantastic answer right here. If you get here and you want to stop, that's great. There's not really anything to clean up like we've had in our previous examples. The antiderivative of t squared minus cosine t dt. And here I show the difference rule. The integral of t squared dt is t to the 3rd over 3 minus the antiderivative of cosine of t, which is sine of t, plus c. What has derivative equal to cosine? Oh, sine does. So the antiderivative of cosine is sine. Don't forget your c, and make sure you use the appropriate variable at all times. It tells you right here what your variable should be. The antiderivative of theta squared plus secant squared theta d theta. Again, we ask ourselves, what has a derivative equal to secant squared of theta? Well, there's a tangent of theta has a derivative equal to secant squared of theta. Therefore, the antiderivative of secant squared of theta is tangent of theta. And of course, we know the antiderivative of theta squared is theta cubed over 3 because we add 1 to the exponent, divide by that new value, and we will never forget plus c. If we have the antiderivative of secant y times tangent y minus secant y dy, remember there's no product rule, so let's multiply through. That's secant y tangent of y minus secant squared of y dy, our integral. What has derivative equal to secant y tangent y? Secant y does. Minus. What has derivative equal to secant squared of y? Tangent of y does. And then plus c is our constant of integration. You're always asking yourself, what has derivative equal to my integrand? And so it makes sense to check it using derivatives. Make sure you were right. Now we have what are called differential equations. And differential equations is a class unto itself. An awesome class, by the way. Some people think of it as Cal 4, and I'm one of those people. But let's have a little introduction to it here and see what's going on. So find the equation of y given dy dx is 2x minus 1. Okay, so a differential equation that has a particular point 1, 1 as part of its solution set, right? This is something new. What are we going to do with that? Well, we know that we can multiply both sides by dx if we treat these as differentials, and we'll get dy equals 2x minus 1 times dx. And we know we can integrate both sides, and we'll get y equals the integral of dy on the left, which equals the integral of 2x minus 1 dx on the right. And we can find the integral of 2x, that's 2x squared over 2. We can find the integral of 1, that's a minus x, well, negative 1, so negative x, and a plus c. Simplifying this, we get x squared minus x plus c. But we haven't used this particular point as part of its solution set yet. What this gives us, it allows us to find the particular value of c for this specific solution. Since 1, 1 is a solution of this equation, we can substitute 1 in for y and 1 in for x, right? X is 1, y is 1. So 1 equals 1 squared minus 1 plus c. 1 squared minus 1 is 0, so 1 equals c. So the general antiderivative, I should take the simplified version, is here. But the particular antiderivative that has 1, 1 as part of its solution set is the equation y equals x squared minus x plus 1. Alright, so we found our function and a particular solution. This all being ones, coincidence, it'll be different in the future. So, same thing. If the derivative is 6x squared and f of 0 equals negative 1, we know that f of x is the antiderivative of the derivative of dx. We know the antiderivative of 6x squared is 6x cubed over 3 plus c. 6 divided by 3 makes 2x cubed plus c. And remember, this is our f of x. So if 2x cubed plus c equals f of x, and our point 0, comma, negative 1, when x is 0, 2 times 0 cubed plus c, this equals the y value of negative 1. 0 plus c equals negative 1, c equals negative 1, and we have our particular solution. Solve the differential equation, same thing, only now the variable is different. Wow, I just totally lost language there for a minute. F prime of p is 10p minus 12p cubed. And we want the particular solution where the function evaluated at 3 equals 2. First step, find the antiderivative. The antiderivative of 10p minus 12p cubed is 10p squared over 2 minus 12. The antiderivative of p to the third is p to the fourth over 4. Simplify and I'll get 5p squared minus 3p to the fourth. And I do a real quick check in my head. If I found the derivative, that's 10p, okay. If I found the derivative, that's 12p to the third. Alright, so I know I'm right there so far. Using the point input 3, output 2. The output 2 is equal to 5 times 3 squared minus 3 times 3 to the fourth plus c. This is 2 equals 45 minus 243, and I have, I was going to say, wow, that was wrong, but I forgot about my 2 over here. Combining these, I will get negative 198, and when I add that to the other side, I'll have a positive 200 equals my c value. Therefore, my particular solution is f of p equals 5p squared minus 3p to the fourth plus 200. See, it doesn't have anything to do with these numbers being one of these numbers, like my first two examples. All right. This one's fun. Solve the differential equation involving trig. I know, you're loving it. It's a McDonald's problem for you. Okay, here we go. The second derivative is sine of x. I know some information about the first derivative. I know some information about the original function. Now, the first derivative is the antiderivative of the second derivative. Right? I'm going to work my way back up instead of using derivatives to work my way down. So the integral of sine of x dx is negative cosine of x plus c. Now, I know this information, this h prime of 0 equals 1. That's going to allow us to find our blue c value here. So using h prime of 0 equals 1, I know my output is 1 equals negative cosine of 0 plus c. Cosine of 0 is 1. If I have 1 equals negative 1 plus c, let's add 1 to both sides, and I'll get c equals 2. I'm going to use this blue value right here. This is my derivative, negative cosine of x plus 2. So my original function is the antiderivative of that, the antiderivative of negative cosine of x plus 2. The antiderivative of negative cosine of x is negative sine of x. The antiderivative of 2 dx is 2x plus a constant. Again, we have information about our original function. Our original function has an initial value of 6, so I can substitute 6 for my function, my output, and that equals a sine of 0 plus 2 times 0 plus c. Well, I know that sine of 0 is 0, so that's nice. I know 2 times 0 is 0, so that's nice. Well, look at that. 6 equals c. So c equals 6. My final solution, h of x equals negative sine of x plus 2x plus 6. All right, so we find our c value along the way. All right, so a particle initially at rest, which is very important, it tells us some good information, moves along the x-axis such that its acceleration at time t greater than 0 is given by acceleration of t is cosine of t. At the time t equals 0, its position is x equals 3. We want to find the velocity and position functions for the particle. Now remember, acceleration is the second derivative, velocity is the first derivative of the original position function. So velocity, antiderivative acceleration. Well, the antiderivative of cosine of t dt is sine of t plus c. Initially at rest. So when t equals 0, my velocity is 0. When t equals 0, sine of 0 is 0. I want my output to be 0, so my constant has to be 0 as well. Once I have my velocity equation, sine of t, position is the antiderivative of velocity. So s of t equals the antiderivative of sine of t dt. Antiderivative of sine of t is negative cosine of t plus c. At the time t equals 0, its position is x equals 3. I probably should have used a t equals 3 there, but go with me on this one. So when time is 0, I know that cosine of 0 is 1. So this is a negative 1 plus c equals 3. Add 1 to both sides, and I'll get c equals 4. And I have my position and velocity functions for my acceleration. Continuing with this example, now I want to find the values of t for which the particle is at rest. The particle is at rest when the velocity is 0. The velocity function was sine of t, right? V of t equals sine of t. Therefore, we solve sine of t equals 0. We know that the sine is 0 for integer multiples of pi. So we would call this, it's at rest anytime we have solutions t equals k pi for any integer k. I believe for my students, this is the last problem on their second to last or the last problem on their homework assignment. So I hope it helped you guys. Anybody else that's listening, I hope it helped you too. So thanks for listening.